The Eifel Highlands, in the last week of November, 1944. What follows is not the story of one identified battery, and no such battery is named in this account, because none needs to be. It is a reconstruction of standard practice, assembled from German artillery doctrine and from the procedures that captured documents and Allied intelligence reports describe. This is how a German field battery of that period was trained to operate, and it is how a great many of them did operate. Such a battery would be in position before first light. 4 guns, dug in on a reverse slope, which means the crest of the hill stands between the muzzles and the American lines. No Allied observer on the ground can see the guns. No Allied observer on the ground can see the flash. The pits are cut into the earth and roofed with cut branches. The spoil is carried away and scattered rather than piled, because a fresh mound of pale soil is the single most reliable thing an aerial photograph will find. From the middle of the war onward, German propellant increasingly included additives intended to reduce muzzle flash, so that even at night, the blast produced less for an observer to fix on. The battery fires a short program, perhaps 4 rounds from each gun, and then the crews begin to hook up. This is the part of the procedure that matters most. German artillery doctrine did not expect concealment alone to save a battery. It expected concealment to buy time, and it expected the crews to spend that time moving. The working assumption was straightforward. The enemy will eventually work out where you are, be somewhere else when he does. A crew that did every part of this correctly could still find American shells arriving on the position before the last gun was limbered. Not ranging rounds walking in from a mile away, not a single battery searching for one. A concentration, arriving all at once from several directions, placed on a piece of ground that no American soldier had laid eyes on. This was not an isolated experience. It is a pattern that runs through the last year of the war in the West, and it produced a specific and consistent reaction on the German side. American official histories record that German prisoners of war, interrogated across different armies and different sectors, gave what those accounts describe as universal testimony to the effect of American artillery. What recurs is not admiration for American marksmanship, it is confusion about the sequence of events. The fire arrived before anyone had been seen. The fire arrived on positions that had never been observed. The fire arrived, in a number of documented cases, on positions that had been occupied for a very short time. A gun crew that has been located by observation understands what has happened to it. Someone saw the flash. Someone heard the report. Someone photographed the tracks. That is a comprehensible way to die, and a German artilleryman in 1944 had spent years learning to prevent exactly that chain of events. What these men were reporting was something else. They were reporting that they had been found without being seen, and an explanation that circulated through the German artillery arm was that the Americans had some device that could watch a shell in flight and read its path backward to the gun that fired it. That belief was not stupid. It was an intelligent guess, arrived at by professionals reasoning from effect to cause. It was also, in 1944, almost entirely wrong. Here is the strange part. 2 years earlier, in North Africa and in the first Italian winter, German batteries using the same doctrine had been very difficult for the Allies to kill. British counter-battery work in the desert was skilled and well organized, and it still struggled. German gunners displaced, and displacement worked. The system that protected them was not a bluff. Against the methods the Allies had spent a generation refining, it was genuinely effective. So the question is not why German artillery was vulnerable. German artillery was, by any professional standard, well handled and well concealed. The question is why a set of survival techniques that had worked for years suddenly stopped working, against an army that was not better at seeing. The answer has nothing to do with sharper American eyes. It has nothing to do with a superior gun, because in several respects, German pieces were the better weapons. It has nothing to do with treachery, though German staffs investigated that possibility seriously and repeatedly. And it has almost nothing to do with the shell tracking device the German gunners imagined, because in the form they imagined it, that device did not exist yet, and would not exist for another 3 decades. It has to do with a physics laboratory at the University of Birmingham, a copper block small enough to hold in one hand, and a question that in 1939 almost nobody thought was worth the money to answer. What happens if you stop trying to see the enemy at all, and instead build a machine that predicts where he will be? The German system deserves to be described properly, because the whole shape of this story collapses if you assume the men on the receiving end were careless. They were not. The German army maintained dedicated observation battalions, the Beobachtungsabteilungen, whose function was the science of locating enemy guns, and, by extension, understanding how their own guns could be located. They practiced two techniques developed to a high standard during the First War and refined ever since. The first was flash spotting, in which widely separated observation posts recorded the compass bearing of a muzzle flash at the instant it appeared, and the intersection of those bearings gave a position. The second was sound ranging, in which a line of microphones recorded the arrival time of the report of a gun, and the differences in those times were used to compute the source. Both techniques were mathematically sound, and both had been proven in combat across 2 wars. The Germans understood the method from both ends, from practicing it themselves and from being subjected to it, and that understanding is precisely why their countermeasures were so specific. Consider what those countermeasures actually were, because each one bears on a particular weakness in a particular method. Reverse slope positions were adopted for several reasons, chiefly protection from direct fire and from ground observation generally, and one consequence was that direct flash observation became very difficult, because a hill cannot be seen through. Flash-reducing propellant additives, in wider use as the war went on, worked on the same signature chemically, dulling it so that even an observer with line of sight had less to take a bearing on. Roving guns, single pieces detached from a battery and fired from temporary positions before returning, were a recognized deception practice, and their effect was to corrupt the picture that sound ranging builds up over time, because the acoustic record now points at a place where nothing lives. Firing programs were often timed to coincide with other noise on the front, because sound ranging depends on isolating one report from the general din, and underneath all of it sat the displacement principle. Every one of the techniques above buys minutes. The German gunner did not need to be invisible forever. He needed to be invisible for the length of time it took the enemy to observe, compute, transmit, and fire. That interval was the entire margin of survival, and German doctrine was built around exploiting it. The most extreme illustration of this thinking sat on a railway line south of Rome. The German army deployed 2 Krupp K5 railway guns against the Allied beachhead at Anzio, pieces of 28cm caliber mounted on rail carriages, capable of throwing a shell far beyond the reach of any Allied field artillery on the beachhead. American soldiers called them Anzio Annie and the Anzio Express, and they believed for a long time that they were dealing with one gun rather than 2. The guns belonged to a railway artillery battery, and their concealment method was the displacement principle taken to its logical conclusion. Between fire missions, they were rolled into a railway tunnel on the Ciampino to Frascati line, some 30 kilometers from the beachhead, inside solid rock, where no bomb and no shell could reach them. They came out, fired, and went back in. Accounts of the battery also describe an additive used in the propellant to reduce the muzzle flash. The tonnage they delivered was modest by the standards of the campaign. By early March 1944, the 2 guns together had fired more than 300 rounds into the beachhead, and over the whole battle, the total ran to several hundred. Their significance was never volume. It was that nothing the Allies did could stop them. Allied air power, Allied naval gunfire, and Allied counter-battery artillery were all directed against them at various times, and none of it destroyed them. A fighter-bomber strike on the tunnel mouth in late May damaged neither gun. They fired their last rounds in the middle of that month, withdrew to Civitavecchia, and were found there in June 1944, wrecked by their own crews during the retreat. One crew completed the demolition, the other did not, because the American advance arrived too quickly, which is the only reason one of those guns survives today in the United States as a museum piece. That is what German doctrine looked like applied without compromise, and it is the standard against which the rest of this story has to be measured. This was not an army that had failed to think about the problem. It had thought about the problem more systematically than almost anyone, and built a set of answers that worked. If this kind of history interests you, the engineering and the doctrine underneath the events rather than just the events themselves, then subscribing and leaving a like genuinely helps. It puts this sort of detailed material in front of more people who want it. Now hold that picture of German competence in place, because the next thing to understand is that for a long time it was not just competent, it was winning. Through the desert campaigns and into the first year in Italy, the Allied counter-battery problem was severe. Allied observation battalions were skilled and their equipment worked, but the arithmetic was brutal. A flash spotting section had to have observers with line of sight to the flash, which reverse slope positions denied them. A sound ranging section needed a clean acoustic record, which meant reasonable weather, a stable wind, and an enemy obliging enough to fire in a way that could be isolated. Then the bearings or the timings had to be collected at a central plotting station, worked through, converted into a grid reference, passed to a headquarters that controlled guns, checked, and ordered as a fire mission. Every stage of that chain consumed time. Not hours if the section was good, but long enough. And the German battery commander knew roughly how long, because his own observation battalions ran the same process against the Allies, and he had seen the stopwatch from the inside. The result was a stable and rather grim equilibrium. Allied counter-battery fire was frequently accurate, in the sense that it landed on the position it had computed. It was frequently useless, in the sense that the guns were no longer there. This part of the war does not get much attention, and the reason is worth stating plainly. The history of the Western campaign is generally written from the direction of its outcome, and its outcome was an Allied victory. A period in which a German technical practice was systematically defeating an Allied one does not sit comfortably inside that shape, so it tends to be compressed into a sentence about difficult terrain. But within the narrow contest of German gun concealment against Allied gun location, judged on its own terms, the Germans were ahead for a long time, and they were ahead because their answer was better designed for the question everybody agreed was being asked. The question everybody agreed was being asked was this: how do I observe the enemy gun? Both sides accepted that observation was the precondition for destruction. They disagreed only about how to achieve it and how to prevent it. That shared assumption is the thing that is about to break. It would be easy, and wrong, to conclude from this that Allied counter-battery work was amateurish. It was not. The United States Army built an entire specialist branch for the problem, and by the end of the war, it fielded 25 field artillery observation battalions containing roughly 13,000 men. These units went ashore with the first American landings in North Africa in late 1942, and were present in every subsequent Western campaign. Their British and Commonwealth counterparts were, if anything, more experienced still, since the survey and sound ranging tradition ran directly back to the Western Front. The men in these battalions were technicians of a high order. Sound ranging required surveyed microphone positions accurate to a few meters, synchronized recording equipment, meteorological correction for temperature and wind, and operators who could pick the signature of a particular caliber of gun out of a pen trace cluttered with everything else happening on that front. Flash spotting required observers who could hold a bearing on a flash lasting a fraction of a second, at night, and report it in seconds. The problem was never the skill. The problem was that the method had been perfected for a kind of war that had stopped happening. Sound ranging and flash spotting reached maturity between 1916 and 1918, on a front that did not move, and everything about the technique assumes stability. The microphone base has to be surveyed in. The observation posts have to be built and registered against known points on the map. Both take time. Given a static front and a few days to prepare, a good observation battalion could build a picture of the enemy gun layout that was genuinely formidable. In 1944, the front frequently moved several kilometers in a day. Every time it moved, the base had to be picked up and re-established, the survey redone, the observation posts relocated and registered again. A section that had spent 2 days building an accurate picture might find that picture worthless by the following afternoon. Then layer the weather onto that. Sound ranging measures a pressure wave traveling through the atmosphere, which puts it at the mercy of the atmosphere. A crosswind bends the acoustic path and corrupts the timings. A temperature inversion refracts sound in ways that are difficult to model. Heavy rain raises the noise floor. Flash spotting depends on seeing light, which means fog and low cloud simply switch it off. And on top of the weather sat the German countermeasures already described, each one aimed precisely at whichever of these two techniques it was designed to defeat. The clearest demonstration of the ceiling on this method is the Anzio beachhead in the first months of 1944, and it is instructive precisely because Anzio should have been the best possible case. The beachhead was static for 4 months. The front barely moved. Allied observation battalions had all the time in the world to survey their bases and register their observation posts, which is the condition under which sound ranging performs best. Allied air superiority over the beachhead was substantial. Naval gunfire was available from offshore, and German artillery shelled that beachhead continuously, from January to May, with an intensity the men who were there remembered for the rest of their lives. Every part of the perimeter was within range of German guns. Soldiers lived underground. Allied counter-battery fire killed German artillerymen throughout, but the shelling was never suppressed, and the largest German pieces on that front survived the campaign untouched by counterfire. There is a detail from Anzio that is worth reporting with a warning attached. The historian Geoffrey Perrate has written that around 70% of the shells fired by German 170mm guns at the beachhead were duds, the consequence of sabotage inside a munitions industry that by then depended heavily on forced labor. That figure is extraordinarily high. It rests on a single account, and it has not been corroborated from primary records, so it should be treated as a claim rather than an established fact. If it is even approximately right, the men in the beachhead were being protected in part by the quality control failures of the German war economy, which is not a form of protection any army would choose. What Anzio demonstrates is not that the Allied method was bad, it is that the method had a ceiling, and the ceiling had been reached. Given ideal conditions, preparation time, air superiority and naval support, the traditional counter-battery loop still could not break a German artillery arm that understood the loop and was designed around beating it. Something did arrive at the Anzio beachhead in February 1944 that would eventually change all of that. 2 of them were unloaded at night, under a blackout, because their existence was classified. They were trailers, each carrying a parabolic dish roughly 2 meters across, and they had been sent to Italy for an entirely different purpose. Nobody put them there to hunt guns. They were there to shoot down aeroplanes. Neither the German artillery arm, nor, at that moment, the American artillery arm, understood what those trailers were the leading edge of. What was arriving was not a better way of finding the enemy. It was the beginning of the end of finding the enemy as the organizing principle of killing him. To understand what those trailers were, you have to go back a decade and a half, to a period when the technology inside them was a marginal interest pursued by underfunded people whom nobody in authority took especially seriously. Radio detection was not an American invention, nor a British one. Several countries arrived at it independently in the 1920s and 30s, because the underlying observation was available to anyone paying attention. At the United States Naval Research Laboratory, Albert Hoyt Taylor and Leo Young noticed in 1922 that a ship passing on the Potomac disturbed a radio signal between a transmitter and a receiver. In 1930, they observed the same effect with an aircraft. The observation was reported. Very little money followed it. The decisive technical step on the American side came at the same laboratory, where Robert Page built a set that transmitted in short pulses and listened in the gaps between them, and where the method of using a single antenna for both transmitting and receiving was worked out. That is the architecture of essentially every radar since. The United States Army Signal Corps pursued its own line under Colonel William Blair at Fort Monmouth, with Roger Colton among the officers driving it forward, and produced 2 sets that were in service when the war reached America. Those 2 sets are worth describing because their limitations explain everything that follows. The long-range set could detect aircraft at considerable distance, and one of them, at Opana Point on the island of Oahu, detected the incoming Japanese formation on the morning of December 7, 1941, at a range of well over 100 miles. The two soldiers operating it reported it. The duty officer at the intercept center assumed it was a flight of American bombers expected from the mainland and told them not to worry about it. The gun-laying set was intended to direct anti-aircraft fire, and it worked, after a fashion. It operated at a wavelength of about 1.5 meters. The long-range set worked at a longer wavelength still, closer to 3 meters. Wavelength is the whole problem. The angular sharpness of a radar beam depends on the size of the antenna measured in wavelengths. A long wavelength radiated from an antenna of any practical size produces a beam that is not a beam at all, but a broad wash of energy. The American gun-laying set had a beam something like 20 degrees wide. Ivan Getting, who would later run the American microwave gun-laying program, described these early sets bluntly. The range performance was acceptable. The angular resolution was not. 20 degrees is a useful number to hold on to. At a range of 10,000 meters, a beam 20 degrees wide is illuminating a patch of sky several kilometers across. You can say that something is out there. You cannot say where with any precision, and you certainly cannot compute a firing solution from it without a great deal of additional guesswork. The obvious answer was to go to a much shorter wavelength, into the centimetric band, where a dish of manageable size would produce a genuinely narrow beam. Every physicist working on the problem in every country knew this. The obstacle was not the idea. The obstacle was that nobody could generate enough power at those wavelengths to be useful. The available devices produced watts where kilowatts were needed, and a radar that cannot put energy out cannot hear an echo back. This was the state of the art at the start of the war, and it is important to be fair about the German position here, because the German decision that would eventually cost them so much was a reasonable engineering judgment rather than a blunder. German radio physics was outstanding. German engineers had examined the centimetric problem and had concluded that it was not practically solvable with the components available, and they turned their effort toward devices that offered better frequency stability at longer wavelengths. Given what could be measured in a laboratory in 1939, that was a defensible call. It was also, as it turned out, wrong by about 2 orders of magnitude, and they would not discover how wrong until it was much too late to matter. The thing that made it wrong was built in a university physics department in the English Midlands by 2 men who were not working on radar sets, and who did not build it because anyone in authority had asked them to. John Randall and Harry Boot were working in the physics department at the University of Birmingham in the laboratory run by Mark Oliphant, on the problem of generating high power at short wavelength. Their solution was a device now called the cavity magnetron. In its essentials, it is a solid block of copper with a ring of cylindrical holes bored through it around a central cathode, the whole assembly sitting in a strong magnetic field. Electrons streaming from the cathode are bent into curved paths by the magnetic field, and as they sweep past the openings of those cylindrical cavities, they excite the cavities into resonance, the way blowing across the neck of a bottle excites the air inside it. The cavities are machined to a size that makes them resonate at the wavelength you want. The result is a compact device that turns direct current into an enormous amount of microwave power. The cross-section of the finished block looks very much like the cylinder of a revolver, a ring of identical holes bored through metal, and it is often reported that the tooling for a Colt revolver cylinder was used on the early prototypes. The resemblance is real, and the story is repeated in reputable accounts, though it is worth treating as tradition rather than documented fact. Either way, it illustrates how far from an industrial program this work was. They ran it for the first time on February 21, 1940. It produced around 400 watts, at a wavelength of just under 10 centimeters. That figure looks unremarkable until you set it against what had been achievable at that wavelength before, which was smaller by a factor of roughly 100. Within a week they had it past 1,000 watts. When the General Electric Company laboratories at Wembley re-engineered it for pulsed operation, output reached the order of 10 kilowatts. This was the missing component. With that much power available at 10 centimeters, A dish a couple of meters across produces a beam a few degrees wide instead of 20, and everything that had been impossible becomes an engineering problem rather than a physics problem. Airborne radar small enough to fit in an aircraft. Ship radar that can pick a submarine conning tower out of the sea return, and a gun-laying set that does not merely detect a target but follows it, continuously and automatically, with enough angular precision to compute where it will be in 15 seconds' time. That last capability is the one that matters here. A radar that reports a position is an observation instrument. A radar that locks on and tracks is categorically different. It produces a continuous stream of numbers about a moving object, and a continuous stream of numbers is something a machine can work on to predict a future position. The moment tracking becomes automatic, gunnery stops being an act of observation and becomes an act of computation. Nobody in the German artillery arm was thinking in those terms, because the device that made those terms possible had been written off in Germany as a dead end. German engineers had judged the centimetric band impractical before the war, and they would not formally close the work down until the beginning of 1943, by which point Birmingham was 3 years ahead of them. In September 1940, Britain sent a small delegation to the United States, carrying a metal deed box containing the country's most sensitive technical secrets. The mission was led by Henry Tizard, and among those who travelled were John Cockcroft and Edward Bowen. Britain at that point was under air attack, short of industrial capacity and short of money. The calculation was that secrets kept were secrets wasted, and that American manufacturing was worth more than exclusivity. In the box, among a great deal else, was a cavity magnetron. The American scientists who examined it understood at once what they were looking at. James Finney Baxter, the official historian of American wartime scientific research, wrote that in bringing the magnetron to America, the Tizard Mission carried the most valuable cargo ever brought to the country's shores. The sentence has been quoted so often it has worn smooth, but Baxter was the official historian of the effort, and he was not given to loose language. What followed was the establishment, in the closing weeks of 1940, of a laboratory at the Massachusetts Institute of Technology, deliberately given a misleading name that suggested it was concerned with nuclear physics. The radiation laboratory began with roughly 30 physicists. At its peak, it employed something close to 4,000 people. It was directed by Lee Dubridge, with Isidore Rabi and Wheeler Loomis among its senior figures, and over the course of the war, it designed in the region of 150 distinct radar systems. Somewhere near half of all American wartime radar procurement traced back to designs that came out of that building. One of those designs is the object at the center of this story. It was given the designation SCR-584, and the work was driven by Ivan Getting, with Louis Ridenour heading the project in its early phase, and Lee Davenport carrying development through to the end of the war. Alfred Loomis, who chaired the committee that funded it, pushed hard for the most ambitious version of the concept, which was a radar that would not merely find an aircraft, but lock onto it and follow it without a human operator in the loop. The technique that made this possible is called conical scanning. The feed at the focus of the dish is offset slightly and spun, so the beam sweeps out a narrow cone rather than pointing straight ahead. If the target sits on the axis of that cone, the returning echo is constant as the beam rotates. If it is off-axis, the echo strengthens and weakens in a rhythm whose depth says how far off it is, and whose timing says in which direction. Feed that error signal to motors driving the mount, and the dish chases the target automatically, producing a continuous stream of range, bearing and elevation. The set operated at around 10 centimeters, in the band between roughly 2,700 and 2,900 megahertz. The dish was about 6 feet across. In trials at Fort Monroe in February 1942, it was locating targets to within about 20 yards in range and to 0.06 of a degree in angle. Compare that with the 20-degree beam of the older set. This was not an improvement. It was a different category of instrument. The output went to an electronic computer built by Bell Telephone Laboratories under Clarence Lovell and David Parkinson, designated the M9. This was an analog machine, a cabinet of servo mechanisms and shaped potentiometers that solved the geometry of a moving target continuously and produced pointing orders for the guns. Radar and computer together formed a closed loop that required no human judgment between detection and fire. The whole assembly was mounted on a trailer, weighing on the order of 20,000 pounds, which meant that in principle it could be moved by road. In practice, as will matter later, it was a large and awkward thing to move. The United States Army Signal Corps ordered more than 1,200 sets in April 1942. Chrysler became the principal manufacturer, with General Electric and Westinghouse also involved, and at peak, the factories were turning out on the order of 200 sets a month. Counting the sets that went to the Marine Corps, to coast defense and to spares, total production came to roughly 2,100. The first sets were landed at the Anzio beachhead at night on the 24th of February 1944. Their effect on the air battle was immediate. On the following night, 12 German bombers came in over the beachhead, and 7 of them were shot down by 90mm guns being directed by the new radar. German aircraft attacking a target of that size, in that confined a space, were now being engaged by batteries that did not need to see them, did not need searchlights, and did not degrade at night or in cloud. German electronic countermeasures of the period were designed against longer wavelengths, and had essentially no effect on a set operating at 10 centimeters, because the German technical establishment did not believe anyone was operating at 10 centimeters. The most famous demonstration came later that year over southern England, against the V-1 flying bomb. The flying bomb was in one sense an ideal target, flying a straight and level course at constant speed without evasion, and in another sense a very hard one, being small, fast and low. When the American radar, the American computer, and the proximity fuzzed shell were brought together in the coastal gun belt, the results changed week by week in a way that is unusually well documented. In the first week, the guns were destroying something like 17% of the flying bombs that came within reach. By late August, it was around 60%, then 74% in the final week of the month, and on one exceptional day, 82%. General Frederick Pyle, who commanded British anti-aircraft defences, wrote afterward, in a newspaper article, that it was the proximity fuse which made the near-total success possible. Those are the numbers that made the reputation of this equipment, and it was precisely this reputation, filtering back to the German side through observation of what was happening in the air, that shaped what German gunners came to believe was happening to them on the ground. So the German inference was this: the Americans possess a device that watches objects moving through the air with extraordinary precision. Our shells are objects moving through the air, therefore the Americans are watching our shells and reading the trajectory backward to our guns. Every step of that reasoning is sound. The conclusion is nevertheless mostly false, and understanding exactly why is the point at which this story stops being a story about a wonder weapon and becomes something more interesting. The Americans did try it, and this is the detail that makes the German theory so nearly right. The set could see artillery shells. It was used to track 90mm rounds in flight over ranges of several miles, but that work was not done to find enemy guns. It was done to gather accurate data on how shells actually fly, so that the firing tables used by every gunner could be corrected. The results went to ballistic research, not to counter battery doctrine. In Italy, the technique was applied against mortars. Operators used a sector scanning attachment to catch a mortar bomb in flight, locked the set onto it, and used automatic plotting boards to extend the observed arc backward to the ground. It worked. Positions were found this way. And Getting, who had every professional reason to claim more, wrote afterward that operationally these procedures were not very significant, for the plain reason that it was impossible to move equipment of that size in sufficient numbers to cover any meaningful fraction of the mortar firings taking place along a front. That is the honest verdict of the man who built the thing, and it should be taken seriously. The British and Canadians went further with the idea than the Americans did. From 1943 onward, British anti-aircraft radar sets were increasingly diverted into what was called the counter-mortar role, and by the middle of 1944, A substantial part of the British and Canadian radar effort in northwest Europe was devoted to it. They used their own gun-laying set, and also the American set, which was the better instrument, and against mortars, they could achieve accuracies in the region of 25 yards. But notice the word that keeps appearing: mortars, not guns. That distinction is physical, and it is the reason the German gunners' theory failed. A mortar bomb is fired at a very high angle. It climbs steeply, rises clear of the ground, and of the clutter of trees and buildings and hills that fill a radar's low-level picture, and follows an arc that is close to a symmetrical parabola. Air resistance modifies that arc, but does not distort its character. Extending it backward is a tractable geometry problem that a mechanical plotting board can solve. A finned mortar bomb also happens to be a comparatively strong radar target for its size, because the fins present surfaces that reflect energy efficiently back toward the transmitter. An artillery shell fired on a flat trajectory is the opposite of all of this. And it is important to be precise about why, because the reason is not that the shell is invisible. The set could detect it. The reason is threefold. First, a flat trajectory keeps the shell low, buried in the ground clutter where the radar picture is at its worst, so a lock is hard to get and harder to hold. Second, the path itself is not a neat parabola, but a distorted curve, much steeper on the descending branch than on the ascending one, deformed by air density, by wind at several different altitudes, and by the aerodynamic behavior of a spinning projectile. Third, and decisively, extending that distorted path backward means solving a full ballistic problem in something close to real time. And in 1944, there was no machine at the front that could do it. A mechanical plotting board can extend a parabola. It cannot integrate a differential equation while the shell is still in the air. The plain statement of the wartime position is that radar could locate mortars, but not guns and not rockets, because although the sets could see the shells, the trajectories could not be solved. The equipment to do it properly arrived long after the men in this story were dead or demobilized. The first purpose-built American counter-mortar radar entered service in 1951, and it needed several rounds and 4 or 5 minutes to produce a fix. The set that could do it from a single round in about 20 seconds appeared in 1958. The British equivalents followed in the 1960s and 1970s. Radar that reliably locates flat trajectory guns is later still, and belongs to the era of digital computing. So the German gunners were destroyed by something. It was not, in the great majority of cases, a radar reading their shells. What was actually killing them was less exotic, harder to see, and far more difficult to defeat. The first element was an aeroplane. Each American field artillery battalion had 2 light aircraft, small high-winged monoplanes of a type used before the war for flying lessons, unarmed and slow. They carried a pilot and an observer with a radio, and they loitered a few thousand feet up behind the front line. From that altitude, a reverse slope is not a hiding place. A reverse slope blocks the line of sight of an observer standing on the ground, and an observer at 3,000 feet is not standing on the ground. The effect of these aircraft on German behavior was profound, and is documented from the German side. Erwin Rommel, writing to his wife in February 1943 about the fighting in Tunisia, described how an observation plane directed the fire of numerous batteries onto every worthwhile target throughout the area. That is the commander who was, at that time, regarded as the finest practitioner of mobile warfare in the German army, and he identified the mechanism correctly, in a private letter, more than a year before the invasion of France. German batteries responded by simply not firing when a spotter aircraft was overhead. That is a rational response, and it was also a defeat, because artillery that does not fire is artillery that is not doing its job. The suppression achieved by an unarmed trainer aircraft, costing a few $1,000s, exceeded anything the Allied bombing effort achieved against the same guns. The second element was organizational, and it had been built at the Field Artillery School at Fort Sill, Oklahoma, during the 1930s, by an army that at the time ranked among the smaller forces in the world and had almost no political support. The innovation was the Fire Direction Center. Instead of each battery computing its own solution for its own targets, a single center held the survey data and the ballistic computations for every battalion within range, and could convert a target location into simultaneous firing orders for all of them. The consequence of that arrangement is the technique the Americans called time on target. Every battery is given a solution and a moment. Each fires at a different instant, calculated so that all the shells, traveling different distances on different trajectories, arrive at the target within the same few seconds. There is no ranging, no walking of fire, no warning. The first indication that a position has been located is the entire concentration landing on it at once. It is worth being clear about what made that possible, because the surprise was not free. Firing accurately without ranging rounds depends on a chain of unglamorous corrections. The gun positions and the target have to be tied to the same accurate survey. The weather aloft has to be measured and applied, because wind and air density at altitude move a shell a long way over 10 kilometers. The wear on each individual barrel and the temperature of each batch of propellant have to be accounted for, because both change muzzle velocity. American practice invested heavily in all three, and it is that investment, rather than the timing trick itself, that let a fire direction center put the first round where it was wanted. Against a doctrine built on displacement, this is fatal. The German battery commander's whole survival calculation rested on the interval between being located and being fired upon. Time on target does not shorten that interval so much as change its character. The location comes from an aircraft that sees the position as it is being occupied. The computation is already done, held at the fire direction center against a map that has already been surveyed. There is no ranging phase to give warning, because ranging has been abolished. The crews are not caught in the open while limbering up, because they were slow. They are caught because the process they were racing against no longer has the shape they were trained to race. The scale this reached in the last winter of the war is difficult to convey without numbers. On the northern shoulder of the Ardennes fighting in December 1944, 348 guns drawn from more than 20 battalions, together with a heavy mortar battalion, were placed under the fire control of a single divisional headquarters and could be fired as one instrument. It is generally described as the heaviest concentration of artillery the Americans assembled anywhere in Europe. In the defensive fighting on that ridge, one day of firing accounted for more than 10,000 rounds from a single type of howitzer alone, and a single mission against 2 villages ran to more than 5,000 rounds in 20 minutes. If you are getting something out of this, a like helps the video find the people who want this kind of material, and subscribing means the next one reaches you. It matters more than it sounds like it should. There is a moment when the German technical establishment discovered how far behind it had fallen, and it is one of the most striking scenes in the technical history of the war. On the night of the 2nd to 3rd of February 1943, a British 4-engined bomber was shot down near Rotterdam. In the wreckage was a piece of equipment that German investigators had not seen before. It was a navigation and blind bombing radar, and it was substantially intact. Telefunken engineers recovered it, and the assembly was given the name Rotterdam Gerät, the Rotterdam apparatus, after the place it was found. When they opened it, they found a cavity magnetron. A study group was convened at Telefunken in Berlin later that same month, given the task of understanding the device and working out what could be done about it. The assessment of its capabilities was written that May by the physicist Otto Hackenberg, who would go on after the war to a distinguished career in radio astronomy. The timing is the part that is almost unbearable. The German centimetric laboratories had been closed at the end of the previous November, and on the 15th of January 1943, the Air Ministry confirmed that the decision was irrevocable. The settled technical judgment was that useful power could not be generated at those wavelengths. They stopped, and then within a month, a working machine that disproved the judgment fell out of the sky into their laps. The consequences of that lost time could not be recovered. Germany did eventually produce a radar based on a copied magnetron, an airborne set introduced in the spring of 1945, in numbers that appear to have been in the region of 25 sets. The war in Europe ended within weeks. It made no difference to anything. The significance for the artillery war is not that German gunners lacked a countermeasure to a shell-tracking radar, because there was no shell-tracking radar to counter. The significance is conceptual. The German army was operating against an opponent whose target acquisition system it could not model, because part of that system rested on a principle its own technical establishment had classified as impossible. When a German staff sat down to work out how their positions were being found, they were reasoning with a picture of Allied capability that had a hole in it exactly where the answer lived. This is why the rumors were so persistent. An organization that cannot model its opponent's method will fill the gap with explanations more dramatic than the truth. The Americans have a device that follows shells. The Americans have someone inside our signals net. None of it was true. The truth was an unarmed training aircraft, a room full of people with slide rules and telephones, and an enormous quantity of ammunition. The second escalation came in the last December of the war, and it removed the final protection that a located gun crew still had. The proximity fuse was a radio transmitter and receiver built into the nose of a shell, small enough to fit inside the fuse cavity, and rugged enough to survive being fired. It broadcast continuously in flight and listened for its own signal returning from the ground or from a target. When the reflection indicated it had reached the right height, it detonated the shell in the air rather than on impact. The engineering problem was severe. The electronics had to survive an acceleration of many thousands of times gravity while spinning at very high speed. German engineers investigated proximity fusing as well, and never produced a working radio proximity fuse for service use. The consequence in the field is a matter of geometry. A shell that detonates on the ground throws most of its fragments outward and upward. A man lying flat in a shallow pit, or crouched behind a gun shield, or sheltering in the lee of an earth bank, is protected by that geometry, and had been protected by it since the First War. A shell that detonates 30 or 40 feet overhead reverses it. The fragments arrive from above, and there is no posture, no gun pit, and no bank that changes what happens next. The fuse had been withheld from ground use for roughly 2.5 years, not for technical reasons but because an unexploded round recovered by the enemy would give away the principle, and the surprise was judged worth more than the earlier advantage. By the time German forces broke through in the Ardennes in December 1944, that calculation no longer held. General Eisenhower asked for the restriction to be lifted on the 19th of December. It was lifted on the 21st. Within days, very large quantities of proximity fuzzed ammunition were moving to the guns, and something on the order of 200,000 such rounds were fired during that battle. George Patton was not a man who habitually gave credit to equipment ahead of soldiers, which makes his written assessment worth quoting. Writing to the head of Army Ordnance, he stated flatly that the funny fuse had won the Battle of the Bulge for them, and added that he was glad they had thought of it first. In a separate report, he described catching a German unit crossing the Sauer River and recorded the resulting casualties by an actual count. Patton was overstating it, and the Army's own official history says so. Proximity-fused ammunition reached the guns in quantity only in the closing stage of that battle, and the fighting had already been decided by other means. What his letter does capture accurately is the impression the weapon made on the men using it, which was that something fundamental about taking cover had just changed. The program behind this was industrial rather than heroic. Something in excess of 20 million of these fuses were produced during the war, at a cost approaching $1 billion, an outlay comparable in scale to the more famous scientific program running at the same time. For the German artilleryman, the sum of it was this: his position could now be located from the air by an observer he could not shoot down and could barely see. The fire that resulted arrived without ranging, from many guns at once, computed before he knew he had been seen. And from the last winter of the war onward, that fire burst above his head rather than at his feet, which meant that the pit he had dug and the earth he had piled were no longer doing what they had been dug and piled to do. Put those elements side by side, and the pattern in the prisoner interrogations stops being mysterious. American official histories record the consistency of that testimony, and the consistency is the most persuasive thing about it, because these were men from different divisions, taken in different sectors, with no opportunity to compare notes and no shared chain of command through which a story could have spread. They were describing the same experience independently, and what they were describing was accurate. They had not been observed by anyone on the ground. The fire had arrived anyway. The obvious question is why the German army did not simply build the same thing. The answer is not that they lacked the parts. They had superb guns and a gunnery tradition second to none. They had observation battalions performing flash and sound ranging to a high standard. They had time-fuzzed airburst ammunition of their own design. They had radio. What they did not have was those things wired together and pushed down to the level of a junior officer with a handset. Several failures contributed. The most straightforward is that by 1944, the Luftwaffe could not keep a light observation aircraft loitering over the front line, which meant the single most effective element of the American system was simply unavailable, and no doctrinal reform could conjure it back. Another is mobility. Despite the popular image, the great bulk of German divisional artillery remained horse-drawn to the end, which constrained displacement and constrained the survey work that accurate massed fire depends on. The most decisive was ammunition. Accurate fire against unconfirmed targets is a technique that consumes shells at a rate only an undamaged industrial economy can sustain. Through the Normandy fighting and after it, German batteries were firing a small fraction of what the guns opposite them were firing, and the gap widened as the transport network was broken up from the air. An army in that position cannot adopt a doctrine of firing heavily on suspected locations, even if it invents that doctrine, because it does not have the rounds. Doctrine is downstream of logistics more often than professional soldiers like to admit. Underneath all of that lay a difference in institutional philosophy, and it is easy to turn that into a caricature, so state it carefully. German military culture placed enormous weight on the judgment of the commander at the point of contact. The principle was called mission-type tactics, and it produced small unit leadership of a quality American and British officers openly envied. American practice moved the other way, treating the man at the front as an element within a designed system, with the judgment exercised earlier in the design itself. Both produced excellent soldiers. Only one produced a network that could put hundreds of guns on a grid reference within minutes, regardless of which lieutenant happened to be holding the radio that day. Now for the correction that has to be made if this account is going to be honest, because it cuts against the direction the whole story has been running. The Americans were not better than the Germans at concealment. They were, on the evidence, worse. American camouflage practice in the European theater was thin. A spotted camouflage uniform was issued to a handful of units in Normandy in the summer of 1944. A few battalions in one armored and 2 infantry divisions, and it disappeared from the theater within weeks. The reason usually given is that men wearing it were mistaken for Waffen-SS troops and shot at by their own side. That story deserves a caution, because a historian who searched the American after-action reports specifically for such incidents did not find them, and photographs show the uniform still in use later than a clean withdrawal would allow. What is certain is that it was tried by very few units, that it was unpopular, and that it was quietly dropped. Nor were the Americans better at the traditional craft of gun location, which the German observation battalions understood as thoroughly as anyone, and the Americans never possessed the capability the German gunners credited them with. That is the strangest feature of this whole episode. The German artillery arm attributed to its enemy a machine that could read a shell out of the sky and name the gun that fired it, and it built its anxieties and its countermeasures around that belief, and the machine did not exist. Against mortars, something like it arrived a decade later. Against guns, which is what these men were serving, it was 3 decades away. The Germans lost to something less impressive than the thing they thought they were losing to. And being wrong about the mechanism meant that every adaptation they attempted was aimed slightly beside the target. Here is the forensic verdict. The gun crew in the Eifel did not fail, their concealment did not fail, their displacement drill did not fail, and it was executed to the standard the manual demanded. What failed was the proposition underneath all 3, which was that being unobserved and being safe were the same condition. That proposition was not a German error. It was the common property of every artillery arm in the world in 1939, including the American one. The German army simply happened to be the most thorough and most disciplined practitioner of a theory that everybody held. The British held it too, which is why British counter-battery work had struggled against German concealment for years. Within that shared theory, the Germans were the better players, and the record shows it. The Americans did not beat them at that game. They stopped playing it. The operative question in American fire direction was not which man is out there, it was which piece of ground is worth a concentration. Concealment is a property of a man and his position. A time-on-target concentration is directed at a coordinate, and a coordinate does not care how well the branches have been arranged over the gun pit. It would be comfortable to describe this as American genius, and it would be inaccurate. It was the residue of 3 unrelated investments that no one coordinated and no one intended to combine. A physics department in Birmingham built the magnetron to answer a question about generating power at short wavelengths, not to find artillery. An impoverished field artillery school in Oklahoma built the Fire Direction Center in a decade when its parent army ranked among the smaller in the world and could barely fund its own ammunition, and built it to solve the problem of massing fire, not the problem of concealment. The light aircraft that did more than anything else to strip German batteries of their protection were civilian designs, built before the war to teach people to fly, adopted because they were cheap and could land in a field. None of the 3 was aimed at the German gunner's camouflage. His camouflage was never the target. It simply stopped being relevant as a side effect of other people solving other problems. The afterlives of these things are not what anyone would have predicted. The magnetron became one of the most widely manufactured devices in history, and almost none of that production went into radar. By the traditional account, an engineer at an American electronics firm noticed during the war that standing near an operating magnetron did unexpected things to food, and within a few years, the same resonant cavity that had directed anti-aircraft fire was heating dinner in domestic kitchens. Even Getting, who ran the program that put those trailers on the Anzio beachhead, spent the second half of his career on precise position finding by radio, and is regarded as one of the founding figures of satellite navigation. The line from a copper block in a Birmingham laboratory to the map on a telephone is direct. And the German doctrine, the one that failed, turned out to be right. The countermeasures the German artillery arm developed, and the displacement principle above all, were not defeated because they were bad. They were defeated by a specific combination of circumstances in a specific period, in which the enemy could see from above, compute centrally, and fire without limit. Once genuine counter-battery radar finally arrived, the machines the German gunners had wrongly believed they were already facing, which for flat trajectory guns meant the digital sets of the 1970s rather than anything fielded in their lifetime, the shoot-and-move principle became the foundation of artillery survival for every army on Earth, and it remains so today. A modern gun crew fires and displaces for exactly the reasons a German battery commander would have recognized in 1944. He was not wrong about the future, he was early, and he was facing the one opponent of that decade against whom his answer did not work. Which returns us to the reverse slope and the battery hooking up its guns in the last November of the war, doing everything the manual asked of it. Men in positions like that one believed a machine somewhere behind the American lines was watching their shells climb and drawing a line back to them. There was no such machine. There was, very often, a small unarmed aeroplane a few kilometers away, flown by a pilot who had seen the vehicles arrive and the guns go into position, and who had spoken a grid reference into a radio. There was a room with maps and telephones where the survey and the weather and the barrel wear had already been worked into a solution for every gun in range of that square. And there was a decision, made years earlier by people who had never heard of the Eiffel, that it was acceptable to spend an enormous quantity of ammunition on a place where the enemy probably was, rather than wait for certainty about where he definitely was. The German theory of survival was a statement about certainty. If I am not observed, I am not hit. The American theory made no claim about certainty at all. It assumed the enemy would usually not be positively identified, and it was built to make that permanent uncertainty survivable by putting enough steel into enough probable ground. Both were coherent. Both were the work of intelligent professionals. Only one of them described the war that was actually being fought. If this account gave you something worth thinking about, a like and a subscribe help it reach the people who want history at this level of detail.